Alright, hello everyone, Mr. Cummings here, and welcome to this video on displacement, velocity, and acceleration. So before we get too far into velocity, acceleration, displacement, all of those things, we want to introduce something called the object model. So in the real world, we have objects that can have weird shapes and structure and all of that. So maybe just like a person who has two legs and an arm, two arms rather. So what we're going to do in physics is, instead of worrying about maybe how this person is moving, or maybe even like rotating or something like that, and worrying about different points like the person's head, the person's arms, the person's torso, as individual things that are moving, instead what we're going to do is we're going to say that this person is a dot. And that dot represents the center of mass of that person, wherever that center of mass is located. And it has the exact same properties as the person, so a mass with symbol m here, not meters, but mass. So we're ignoring all of the size, the shape, the internal properties, and all of that. So let's look at an example here. Let's say that we have some cart that has a length of 0.2 meters and a height of 0.1 meter. And the cart's located at some initial position x equals 0. So let's call x equals 0 here this beginning of this line. So over here we have the actual drawing of the cart. And it's not really clear what do we mean that the cart is starting at some position x equals 0, starting at the origin. So by saying that the cart is located at x equals 0, is it saying that the cart is located with the front touching 0, the center touching 0, the back touching 0? It's not really clear, and now it doesn't really change the physics of the problem, but it's much easier to say that the cart, the center mass of the cart, is located at x equals 0. And when we do the object model, that's really what we're dealing with. So we're dealing with a dot representing the cart moving instead of the whole cart moving. This is what's actually happening in reality. This just makes the physics a little bit easier to visualize. So now getting into the difference between velocity and speed and introducing both of these terms. So they sound similar, and in our everyday life we probably use them interchangeably, but in physics they are quite different. So velocity is a vector quantity for one, and speed is a scalar. So velocity has magnitude direction, scalar only has magnitude. They have the same SI units, so measured in meters per second. But velocity describes how fast something is going and what direction it's going in, whereas speed describes how fast but not the direction. So an example down here, we know that something is a velocity if it says plus 3 meters per second, or if it describes maybe 3 meters per second in the rightward direction, whereas a speed maybe would just be indicated by 3 meters per second, not telling us which way it's going. So let's introduce the concept of average velocity. So an average velocity, if an object's velocity is changing over time, if its average velocity would be calculated using the initial and final velocity values. So if you think about how we do an average, over here to the right, we can say the average velocity would just be two velocities, the initial and the final velocity, v subscript 0 plus v subscript f, so the initial and final. If we wanted to know an average value, if we have two of these, we're just going to take those, add them, and then divide by 2, just like we would by taking the mean or the average in math. But we also get a different equation in physics, where average velocity is the total displacement over the total change in time. And that's indicated by this equation down here. So if we take a look at an example problem, we can use these two equations in conjunction with each other to find some interesting information about something that's moving. So let's say we have this toy car. It's initially at some starting position, and it begins constantly accelerating, and in the negative direction. So we're accelerating in the negative direction. So at time t equals 3, the cart's located at this position x equals -9, whereas at the initial time we're located at the origin. So if we wanted to find the average velocity here, we have a change in position occurring over a change in time, so it would make sense to use this equation as opposed to the top equation because we don't have two velocities to figure that out. So you see we've broken up the delta x to x final minus x initial according to our definition of displacement. And we've done the same with time. Now just plugging in the values, we can calculate what this average velocity will be. So we're going to get that our average velocity is 3 meters per second in the negative direction. Now we can use this in conjunction with our top equation to figure something out about the final velocity, now that we know the average velocity. So what we're going to do is read through this problem one more time and note that the object does start at rest, which tells us our initial velocity is 0. So what I get is that my final velocity is negative 6 meters per second, whereas my average velocity over the entire course of time is negative 3 meters per second. And so that brings us to our takeaway here. Average velocity is not the same as something that we call instantaneous velocity. So we saw that the final velocity was not equal to the average value. Something else to note here is that for objects starting from rest and constantly accelerating, the final velocity was twice the average velocity. So let's take one more look at an example where we're going to actually use the shortcut VF equals 2 V average. So we have a similar situation to the previous problem. We're starting at rest, and we have the same starting conditions. We're now accelerating in the positive direction instead of the negative. And we're traveling for 4 seconds, and we move to some final position 10 meters. So to figure out our average velocity, it looks like we're still going to use the displacement over time. So our change in x is from 0 to 10, which is going to be positive 10 meters. And our time here is 4 seconds. So we're getting 2.5 as our average velocity. And now we can use the shortcut, now that we know our average. Our final velocity after traveling for 4 seconds should just be 2 times that value, 5 meters per second. So thanks for tuning in to this video on displacement, velocity, and acceleration, and I look forward to seeing you next time.